Nice to be in orbit.
And so my job, and I got the funding for 10 years, was to find a way to make this commercially viable in a commercial fab at commercial yields so the military could use it. So we did that. What we ended up with is what we call ultra CMOS, which is sometimes 1,000 angstroms, sometimes only 600 angstrom thick layer of near virtually perfect silicon, sitting on the world's best RF substrate, Sapphire. And when I started the company, I thought, don't get in the way of CMOS. We'll never break in. We can't keep up with digital. So we have to do something that's different. We have to rely on the silicon is there, and it's just going to be CMOS. We have to differentiate ourselves on the substrate. And the two properties of Sapphire that I really liked were it is literally immune to all RF signals. It doesn't create distortion. It can't conduct current. It was a perfect RF substrate. It was also optically transparent. So we looked at, should we be kind of in the display business or the RF business? RF sounded like integrated circuits. Displays didn't. So basically, it was almost arbitrary. I just believed there was a bigger market in RF. So that was what we decided to do with the technology that we developed at the Navy lab over about 10 years. Here's how we did it. This is the work getting from here to here is what we actually developed at the Navy lab. If you grow silicon on Sapphire, it turns out it's not a crystal match. All of those defects had all sorts of side effects which were really problematic. If these defects got up to a gate oxide or if they caused problems with a threshold over the sizes of the chips, you just ended up with a 5% yield. I mean, look at this stuff. Imagine trying to make a Pentium in anything that looks like that. It's just unimaginable. So we set out to fix this, and we used an invention made by HP. Worked with the HP inventors. They had decided to get out of this business, so we picked up the work. And basically through a process called SPE, solid phase epitaxial regrowth, what we did was we learned the recipes that said if you implant silicon in here and destroy all the crystallinity. The good news is you got rid of all the defects. The bad news is you got rid of all the crystal. So what do we do now? Well, it turns out if you heat it up, and the only reason we're here today is nature threw us a bone. It turns out what we want is 100 silicon. And the growth rate of the pieces of 100 silicon in between all these defects is 10 times higher than the growth rate of the defects. So all you had to do was heat it up. And the fast good stuff grew faster than the slow bad stuff. So we ended up with a nice lawn of thick grass, and all the crab weed was down, and we never even saw it again. Then we did a second implant deep enough to get rid of the defects on the bottom. Same process to have it grow down till it hit the Sapphire and it stopped. We turned on steam, which turned silicon into silicon dioxide, strip it off with hydrofluoric acid, and voila, you have bulk silicon grade silicon on a perfect RF substrate at any thinness you want, because the thickness was controlled by the oxidation step, not by deposition accuracy. And oxidation is the most controlled, thermal processes are the most controlled processes in the silicon system. So we got from here to here. We now have this material. It's very, very thin, which means we can scale the transistors, because transistors have to be at least 1/5 as thick as they are long, wide, whatever you want to call it. And so if you want to make a shorter transistor, you got to have a thinner silicon. This stuff didn't work because the thinner you got, you can see the defects are even worse down here than they are up here. So the thinner you got, the worse it got. This stuff fixed all of that. And that was when basically Graham Garcia, Mark Bergner, and I published a paper and essentially said we think we fixed silicon on Sapphire. That's in our history monograph out there. That's what we're calling the aha moment. That's when I realized the technology was fixed. We did what all those companies hadn't done with 6 researchers in a buried government lab, literally underground. And we actually had done something the industry hadn't done. And I started thinking, maybe this technology deserves one more chance to win in the commercial market, which is exactly why I decided to start the company. So what's the advantage for RF? Well, this is what a bulk silicon transistor looks like in cross-section. And everything everybody likes to talk about is the channel between the source and the drain. This turns on if you put a nice high voltage on the gate. You invert the device and you create a conduction channel. You have an N+ source, you have an N+ channel, you have an N+ drain. Guess what? It can't put voltage on it. It'll conduct like crazy. It's That is the magnificent MOSFET, whether it's P-channel or N-channel. The problem is that to keep these devices isolated from each other, basically most people use what's called junction isolation. So if you put plus, say, 3 volts on the drain, there's a depletion region formed in the P region. The 3 volts all ends up terminating down here, so the substrate never sees that voltage, which means the neighbor doesn't see it. So if Bob Noyce had survived, he would have gotten the Nobel Prize but he died. You can't get a Nobel Prize when you're dead, only living people. So everybody knows he was the half inventor of the integrated circuits. He just didn't last long enough to get the prize. But these capacitors, one of the big problems, and I'll get into what happens here, capacitance of a diode goes as 1 over the square root of the voltage. In other words, it's a nonlinear capacitor. People try to use them for varactors, and you use them in ranges where the nonlinearity gets dealt with, and you dope things, but the fact is it's nonlinear. It's not a linear capacitor. And that turns out to be critical to why Peregrine has succeeded, because if you go from this device, and there's 3 of them, one under the gate between the channel and the bulk, one between the source and the bulk, and one between the drain and the bulk. The conduction channel has this term in it, which I'll get into, as well as the capacitors. If you look at what we have, all of those nonlinear capacitors are 0. If they were there, they'd be nonlinear. It's just that they don't have the other side of the capacitor. They're gone. The other term that really causes problems in linearity, and those of you, many of you are in the RF and wireless markets, linearity is absolutely the magic elixir of modern communication system. It's why Broadcom is here. It's why Qualcomm is here. It leverages spectrum. If you have a linear system, you can get more data down the same path as you can, as long as you don't disobey Shannon's law. That's what Shannon's law actually says. But you need linear systems to exploit that, and that's why we have 8-bit QAM and then 32 and 64, et cetera, is we're trying to get more data into the same spectrum. And that comes from linearity. Linearity is king. So what we need is a really, really linear transistor, and guess what? The inherent current in a MOSFET has 3 basic terms. A times the linear voltage, B times the square of the voltage, and then this funny term that's the third 1.5 root of it. Well, it turns out if you take the third derivative of this term, guess what? That term and that term go to 0. Third derivative of V squared is 0. This term you never get rid of. You can keep taking the third derivative, the 10th derivative. It'll never go away. But if you don't put any doping in the channel, which is what N sub A is, in other words, you have what is called a fully depleted transistor, which is what we focused on from day 1. If there's no doping in the channel, N sub A is 0. So the capacitors are 0, the N sub A term is 0, the V and the V squared term are 0 to the 3rd order. And therefore, when we launched the company, we had people like Steve Moss, who many of you probably know, Mr. Mixer worldwide. He stood up at European Microwave. His annual State of the World for Mixers speech, he got up and he said, every year I come here and tell you how to get a ½ dB better mixer. I have 2 words for you, Peregrine Semiconductor. They've moved the mixer bar a decade or more because their transistors, as far as I can tell, I cannot find the linearity limit of these transistors. I'm measuring the linearity of the spectrum analyzers and the test equipment. In fact, it wasn't long after that we sold 1 million mixers, and they all ended up in test equipment because Agilent and Rodian Schwartz and everybody else found out the same thing. By definition, test and measurement people have to use the best components, or you're only measuring the test and measurement equipment. So with that, now I got to be honest, I didn't know what linear was. I'm transistor weenie. I had no idea. And we hired a bunch of RF guys, and one guy came in and he said, well, I'll work for you. I think the company's, but before I sign the document, I want to go in and measure the linearity of your mixers, of your transistors again, to make sure that I measured it correctly the first time. Because if your transistors are that linear, I don't know what we're going to sell, but we're going to make a lot of money. And I waited until he signed because I didn't want to scare him away. And after he had signed the offer letter, I said, Rob, what's linearity? And he started looking for the paper. But it turns out, and this gets back to that, don't be afraid, do something, believe something may come along. We had a great technology, I knew it, and I didn't know why. But that wasn't a reason not to get going. We would have never discovered that if we hadn't gotten started and started interacting and looking for what products to make and how to make them and who's going to buy them and what's the benefit, et cetera. For those of you who are circuit model guys, basically this is all the substrate stuff in a bulk silicon transistor, and that's all 0 for us. So that's where all that linearity comes from. And basically this right here is the problem with MOSFETs. G sub M sucks. The best transistor nature ever gave us is the bipolar. It's beautiful. It has great gain. It has absolute threshold match, VBE. It's wonderful. It can handle power. It's just a magnificent transistor for everything except switching, because it saturates. You can turn them on fast. You can't turn them off fast. And so while G sub M is terrible compared to a bipolar, we had this switching transistor called CMOS, and now it was linear. And we knew we could do something with that. And that's basically, and the good news on a MOSFET is G sub M, it goes as 1 over gate length. So if you scale, G sub M gets better. Scale more, G sub M gets better. Well, to scale, you got to have thinner silicon. Oh, that's right, the silicon's perfect. So we had this, what our CEO now, Jim Cable, calls Moore's Law for RF. We can do everything in RF, and if we don't have good enough gain for an LNA, scale it. Go get a shorter gate length. The world's full of fabs that are way shorter than what we're using today.